Hello everyone. In this video I would like to do some theory, and that is about armature reaction in a DC machine. So there is some phenomenon that is happening in the DC machine due to which there is some armature reaction, like there is some reaction to the magnetic field due to armature. So what is it and how it works and what do we do about it, all that things we are going to discuss very shortly now. So let me begin by drawing the magnetic field of a two-pole DC machine. So if you know the basic construction of a DC machine, only two poles, so you find that there is a north pole here and then there is a south pole here. So this is roughly the magnetic field of a two-pole machine. Then the magnetic flux lines can be drawn something like this. So the flux is flowing from your left side to right side. In between there is an armature. So this is armature. And armature will have armature conductors. So let me just show them. This is a cross-section view. So you will find the conductors are, the cross-section of the conductor is a circle. You will find something like this. So how do we represent the magnetic field of the DC machine? So it can be represented as a vector which is like this. This is Fm, magnetic field of a DC machine. So the direction it is showing from left to right, and you can also say the length of this will be the magnetic field. So the more ampere turns are given in the field winding, the more flux is generated and the more flux will be there. So the point is, for this particular configuration, the magnetic field is from left to right. Now what happens? We will also define an axis like this. So this axis is called GNA, which is geometrically neutral axis, which means considering only the geometry, that means something which is exactly dividing the north and south poles into half. This is done. The same axis can also be called MNA, which is magnetically neutral axis. So magnetically neutral axis and geometrically neutral axis, they are all coinciding with each other. So what is magnetically neutral axis? Nothing but on this particular axis, it is exactly in between the north and south pole. The magnetic field is parallel to the conductor. So the conductor is moving from left to right, magnetic field also moving parallelly from left to right. So in this conductor, the EMF induced will be zero because it is not cutting the magnetic flux, both are going parallelly. So imagine like two cars are going parallelly, they are not cutting each other. But then if there is a crossroads and then the car is coming this way, then another car is coming this way, then they are cutting each other. And EMF is induced only when the conductor cuts a magnetic field. So therefore here EMF induced is zero. So the property of magnetically neutral axis is nothing but EMF induced will be zero at that particular axis. And the property of geometrical neutral axis is that it is basically geometrically in between them. Alright. Now what about the current carrying conductors? So there will be a load connected, there will be a brushes. So I just draw the brushes here. Actually the brushes will be placed on the commutator, but just to logically show the position, the brushes will be placed where the EMF will be zero or on the magnetically neutral axis. And the current can be assumed to be like this. So you know that whenever you notate by giving a cross, that means current is going into the machine. And then when the notation is a dot, that means the current is coming out of the book in this example, or out of your screen if you are seeing on the screen. So now the current carrying conductor also has a magnetic field. So let's draw that. So this is main field. So this is number one. And number two is armature current field. So magnetic field due to armature current. So let me draw the armature and let me draw the armature conductors. So on the left side, the current is cross. On the right side, the current is dot. Now what will be the direction of the magnetic field? So using corkscrew rule, you can draw the direction of the current. So the corkscrew rule says that if you have a screw like this and then you rotate it, if you drive it into the page, you rotate it clockwise. So the field is like this. So similarly, if you add all the magnetic fields of all these things, you will get a resultant field something like this. So of course this join from the outside. So if you focus only on the armature, the magnetic field is going downwards in the armature. Similarly, look at this. Here the current is coming out of the field, so the magnetic field will be like this, because you want to, using corkscrew rule, you can again find the direction that way. And if you want to find the resultant field, it will be something like this. So this will pass through the windings like this. So in effect, if I want to represent it using one resultant force or as a resultant vector, so this will be Fa. So Fa is downwards from top to bottom, whereas Fm is from left to right. At any point of time, both magnetic main field is, in this drawing we just draw only main field, in this drawing we just draw only armature current, but then both together exist. So let me draw the third diagram where I do the combination of these two. So if both the fields are together present, what happens? So if you see inside, the field is like this, here the inside the field is like this. So let's do some vector addition. This is Fm and this is Fa. By the way, what about, this is the directions are like this, 90 degrees. What about the length of this Fm? By putting more conductors or more current in the field winding, I can generate more flux. I can control the length of this. I can what about the length of the Fa? So Fa is proportional to, the field due to armature is proportional to armature current, which is nothing but dependent on the load. And as a generator, load is not under our control. As the load increases, armature current increases and this Fa increases and so on. It depends on the load. So what is the resultant of these two? The resultant of these two is something like this. Fr, let's call it resultant. So if I draw a diagram, it will be something like this. So the 1, 2, 3, 4, 5 lines or 6 lines I draw from here. So 6 lines I draw from here. So by the way, when I draw the lines like this, there might be 6 billion lines or some hundreds of millions of lines here. I'm just drawing only few flux lines as a representation. And Fr is the resultant flux, should be like this. So therefore, what happens is something like this. So because inside the armature, I should be parallel like this. And then once it comes out, be like this. So one more line, then I join it like this. So this is the direction of the flux lines. So this is the effect of, so one was only main field, 2 is armature field due to armature current, and 3 is the combined effect. And this is what is armature reaction. Okay. So due to armature reaction, you see the field is rotated by some angle. Now, what about our axis? So if I draw a straight line, this is still geometrically neutral axis. But then the magnetically neutral axis, the axis where the conductors are moving parallel to the flux, is this one. So this is where EMF is 0. And this is your magnetically neutral axis. And let's denote an angle theta. So this angle is theta. So theta is angle between MNA and GNA. Okay. Now what are the implications of this? So if I draw some conductors here, so because of the shifting, so if my brushes were still here, at the time of brush connecting here, there will be still some voltage in the conductors, and when the brush moves from one capacitor commutator segment to the another commutator segment, there will be sparking. So to avoid this sparking, the brush position must be rotated by theta degrees, so that I am able to change the connections when the EMF is 0 in this and current is 0 in this. At the time if I do it, then the sparks will not be there. So that is the first effect of armature reaction. Now if I ask a question, is this theta constant? Is like theta is 10 degrees or theta is 20 degrees? No, it is not like constant. It is dependent on load, so proportional to load. So if the electrical load on the generator increases, then more current will flow in the armature and more distortion of the field is there, and therefore theta is more. And therefore the brush position has to be continuously shifted in the machine depending on the load. So for example, if the load is electrical load is like, let's say 50 lamps, 50 lighting lamps. So in that case, let's say it is 10 degrees theta. If I increase, maybe if I make it to 100 lamps, so then it might go to 20 degrees. Although the relation may not be linear all the time, but then I'm just giving it as an example. So all the time the load is varying, therefore all the time the theta is varying, therefore all the time you need to keep adjusting the brushes. So I imagine maybe in the olden days, whenever maybe some person might be sitting beside the machine, whenever he notices some sparking is there, he would maybe move or rotate the brush position so that the sparking is reduced. Now there might be some automated controllers for that. Anyway, so let's continue our discussion. I think I'll draw one more diagram, and this one more diagram is about the currents. Okay, so assume that there is a brush here now. So therefore the currents in this part will be still cross, and the currents on the right side will be dot. So due to that, the armature field will be something like this. So because all the conductors on this side has the cross, and all the conductors on this side has dot, so it's not magnetically, this is magnetically neutral axis, sorry, this is GNA and then this is MNA, and this angle is theta. So these conductors, because they are carrying current in this direction, the magnetic field will be like this. Okay. So this one will be FA. So earlier FA was exactly down, but because of shifting of the brushes and because of the armature reaction effect and all, now the FA is slightly moved like this. So this FA can be split into two components. So let's call this FAD and FAC. I'll just come to it why I'm using this terminology. So you notice what is the relation between FAD and then FM. So they are opposite each other. So this is FM and this is FAD. So this is nothing but demagnetizing flux generated by the armature, demagnetizing flux. Whereas FC, you notice it is exactly crossing this one, so it is distorting. So this FAC is nothing but cross magnetizing flux. So the net result of armature reaction I have tried to summarize in this video. This is a short video. First video we draw the main field in the first figure. In the second figure we draw only the armature field, and then the third figure we draw the combined field, and the result of that is that we are getting a demagnetization of the flux and then cross magnetization of the flux. Now the question is, how do you address this? The way to address this is if I connect a winding in series with the armature winding, so that the current in this winding, there is already a shunt field winding here. This is our RSH. This one is what is called as armature compensating winding for compensating the armature reaction. Now if this current is in series with armature, it will have the same current as that in the armature. So the variations of that it will consider, and then it starts strengthening the field. So the ampere turns, that is FAD. So we have FM, then we have FAD, demagnetizing effect, and then we have maybe C, compensating, FCF or whatever, compensating field or whatever. I'm running out of symbols here. So these two would cancel out each other and then there will be a main flux. So that would be good. By the way, we would like to maintain the main flux because the EMF generated is proportional to the flux. So if there is a demagnetization effect, the less EMF is generated, which is not good for working of the machine. So I hope there are also ways to affect the cross magnetic flux. I'll tell about that in the next videos. Okay. So with this, I'll try to end this video. So let's see more in other videos.